Usually I give talks about what features C++ has and how they can be used well, and a bit about why they're there. Today is a little bit different. I'm going to talk about the design principles, design ideas, and that has guided the evolution of the language, and how it came about to the state we have today. I mean, if you look at this slide here, there's a lot that's been going on over the years, and it is somewhat amazing that it's still going strong over 40 years with from one person to more than 5 million developers. And there's been ups and downs and such, but we have to evolve it. Okay, so basically, I heard Dennis Ritchie say once there was languages designed to solve a problem, and then there was languages designed to prove a point. He did not like the languages that was designed to prove a point. And C and C++ was definitely designed to solve specific problems. For C, they needed to write Unix, and with C++, I wanted to build a distributed Unix. And I soon found out that I couldn't do it. There was lots of reasons for that, but the reason I settled on was there was no language that allowed me to do what was absolutely necessary. I needed something where I could write my device drivers, memory managers, process schedulers, and things like that. Low-level language. C was quite good for that. But I also wanted to be able to say that these components of a system, distributed or a network or something, there's a bit here and there's a bit here. How do you define those bits? And they talk using some kind of protocol. How do you specify that kind of protocol? So I needed two things. There was languages that could do the former, languages that could do this latter. And so I had this idea to take similar style classes that allowed me to organize my code and put it into C and make it run fast enough to use for really hard systems programming. But there also was a couple of ideas in the design of this merger, was that I really liked a completely safe and extensible type system. Especially the extensible things was important, something I'd learned from Simula, object-oriented programming, or for some definition or other. I'd actually been taught that by Christian Nygaard, who invented object-oriented programming. And I wanted the optimal performance from C. I mean, I used to say not a byte, not a cycle. And getting those two things together turned out to be hard. So basically, to this day, C++ rests on two pillars: a direct map to hardware, something that started with C, and that is extended to unusual hardware. Hardware is getting weirder and weirder every year we see, and the language has to deal with that. And zero overhead abstraction, so that we don't have to deal directly with hardware all the time, because that is not productive and it is not reliable. So one thing that I keep in mind is that this is not a mathematical exercise. It's also part of mathematical exercise, but it's not fundamentally. It is about people. Code is written by people for people, and when we forget that, we can write very fancy academic papers, but it doesn't actually help that many people directly. And so in the C++ programming language that I wrote and published in '85, the first sentence was C++ is a general purpose programming language designed to make programming more enjoyable for the serious programmer. Serious programmer was my way of saying people who write code for other people, so that they have to depend on it. And basically you have to remember that writing code, designing systems is a human activity, and you have to keep that in mind, and I try. So the other thing is that all forms of engineering relies critically on feedback. So designing a language, which is a tool for building things, you have to have feedback. It is the engineering part of it. And basically, you have to evolve to cope with new problems, and you have to have the design decisions guided by real-world problems as opposed to fashions, and there are lots of those. So basically, once you start designing at a certain scale, you have to articulate your principles. You can't just have the principles in the head of a designer or a group of designers. Somehow they have to be articulated. And I did that sometime in the early 90s, relying on things I built up from before that. So you have a selection of design rules from the book I wrote at the time. And you can see that type safety, expressive type system, direct use of hardware, zero overhead abstraction, and abstraction in generality is there. And I wish more people had understood this, then our code would have been much better today. But at least we tried, and that was one of the things that stopped C++ from sort of evolving into something really strange that wasn't particularly useful. Now, once there's a certain amount of success for a language, lots of people come and tell you that they want something more. I mean, we all want a simpler language. We all want a more powerful language, more expressive language. And also, a lot of us who build things that has to last for decades want stability. Stability is a really significant fundamental feature. It's not just something that's a pain in the neck, which it also is. So a typical request I get maybe twice a month is, we really want a simpler C++. You must simplify C++. And why you do it, add these two features. They're essential. You must do it. And whenever you do, don't break my code. I have 1 million lines of it, and I can't afford to rewrite it. And this is a fundamental, what's it called, dilemma or trilemma or something like that, which we have to solve. One of the solutions is actually to generalize and provide simpler ways of doing things that become important over time. So another question is, why should we evolve? Why don't we just grab a new language and write everything from scratch in it? Well, I can think of a few billion lines of code as an argument, but also the simple fact that it has to last. And our programs change, and we change, we learn how to do things better, and we have to reflect that in the language, and we just can't change our language every 5 or 10 years. Well, students can, but people who develop systems that has to last for a long time cannot, and the world really does change. I mean, those two computers are to scale almost. The little one at the bottom has been enlarged so that you can see it properly. So after a while, design processes become difficult, they become more formal, they involve more people. It is not just a single person or a small group that can do that. So one year, 1989, representatives from IBM, Sun, and HP came into my office and basically twisted my arm mercilessly, saying, you want to help us standardize C++ under the ISO rules of standardization. And I, of course, say, we're not ready, I'm still experimenting, And they said, no, you don't get it, Bjarne. We cannot use a language that is controlled by somebody like AT&T that you work for. We trust you, of course, but you might get run over by a bus. So I agreed after a while, a lot of arm twisting, and we've been working under the rules of ISO ever since. And that's why we can do all of these things. We don't have a rich owner, never had a rich owner. The largest amount of money I've spent on marketing was $5,000. Actually, I could only figure out how to spend $4,000 because it's such a small amount, and we had a really great party. We haven't had an option for dictator for life. That's not under ISO rules. And we can't have everybody contribute equally, because then you have total chaos, so it has to go through a design process. And basically, that's it. This is not my idea. In retrospect, it would be much nicer to have a small secretariat of people that are experienced, insightful, can learn, can experiment, things like that, supported by a large active community. One problem is somebody has to pay for such an organization for decades, and I have never figured out how to do that. So what we have is a standards committee. This is a picture from Prague from 2 years ago, when we managed to get the standard C++20 out just before COVID hit. And so when we talk about features of C++, remember, you have to get all of these people to vote strongly in favor. We don't go for 52 versus 48 kind democracy. We go for consensus, and we really prefer sort of 90% in favor. The national bodies that votes on this in the end has never voted less than 21-0 for one of the standards. So that's good. What the standard brings us is some stability and some vendor neutrality. So you can't break any significant amount of code for those people, so we won't. And no organization can sort of twist the arms of that many people, insightful, hard-working people, so we don't get that. So basically the organization is like that. You can look it up on isocpp.org. But there's 4 working groups, 19 study groups, 4 groups looking for sort of cross-cutting issues like security, performance, and a direction group that tries to formulate rules and how to go about things and ideals. Almost everybody is from industry, and that has always been the case. C++ was born at Bell Labs, which was an industrial lab at the time, and that's what it is. 17 nations turn up at meetings. That was physical meetings. Now they are meetings in sort of virtual meetings somehow, and lots of smaller focused meetings. You can find all of our documents online. Search for WG21 and you will find all the papers back to 1990. It's more than anybody could possibly want to know about C++. Okay, there is lots and lots of problems. This is at least as hard as designing any of the language features or library features. It is just stopping the language process, the design, from getting unbalanced or fractured and things like that. We haven't been able to do face-to-face meetings, so we're a little bit less ambitious for C++23 than we used to be, because there are issues like fundamental design issues and principles that are hard to do on a Zoom call. You have to be in the room, you have to see how people react, you have to be able to talk about it. But there is lots and lots of things like that. There's a lot of single issue interest that has to be balanced for overall language concerns. So what we have is a problem of avoiding design by committee. Really, that is designed by a confederation of committees, and we've sort of, we haven't done too badly, but it's non-trivial. So let's look at some practical problems that we've faced. One of the really early ones is that I wanted to build an operating system kind of thing, and that means that resource management is an absolutely critical part of whatever is going on. And so looking at what's a resource, it's something that you acquire and you have to give back. Memory, file handles, locks, transactions, shaders, sockets, the list is going on and on. And basically, resource release must be implicit and guaranteed. Any librarian would tell you that people take out books and then they forget to hand them back. It's not just memory, it's not just library books, it's just anything that you have to remember to give back. Unless something helps you, and then you will forget. And so it has to be general, There's memory, and there's other things like database transactions and shaders and things like that. They're not memory. A garbage collector is not going to solve the problem. And it has to be predictable and prompt, because, well, I was thinking of systems that was things like device drivers. You have to have performance, otherwise you don't have a use there, because then you write in assembler or something else. And no dependence on significant runtime support, because, well, there's not much memory on all systems. Some systems have very little. So the earliest C++ looked a bit like this. Syntax have slightly changed. The only time I broke the syntax really badly was just when I renamed C with classes to C++. Since then, code like this has worked. You have a constructor that creates an object, acquires necessary resources to operate, establishes invariants and things like that, and then the destructor there with the twiddle that basically re-establishes whatever situation was before you came in. It releases resources and such. And then this came into C++, what became C++, in about first or second week of development. This is the real core of C++. And then you have access functions, and what you're doing is you're going from one level of abstraction. Here, this is just the basic memory pointers, which are basically machine addresses and integers, and you lift it to something that has proper copy semantics, and you could potentially do range checking of access and things like that. So this is how you raise the level. You do it by defining a new type with the proper operations, with the key being the constructor and destructor, and now I can create an object, I can use it, and when it goes out of scope, all resources owned by the memory is released. Okay, this is memory management, but it generalizes. So here I have a finally. It's a function that you give another function and says, at the end, kindly call this function. And the implementation is there. The constructor for final action takes the operation you give it, stores it away, and the destructor calls it. This is not rocket science. And the effect is, I can say here, finally call goodbye cruel world. And so here I say hello world, and right here the destructor is called and it says goodbye cruel world, like that. I put in here, this is from C++ 17, I think, no discard, so that you couldn't forget to store the result of the finally function somewhere. So this is my answer to people who says C++ should have a finally. It has. It has had it for 20 years. Okay, the RAII, as this was called, resource acquisition is initialization, which is a very clumsy term, which sort of illustrates why I shouldn't be in marketing. I was very busy that year. So all the containers in the C++ standard library follows this pattern, and there are other things that are not just memory, threads, I/O streams, locks, and such, and it all works recursively. Of course, you tend to have a handle, you have to have a value, you have to establish this pattern in the constructor. In destructor, you clear out anything that needs to be released. So garbage collection is neither sufficient nor ideal, and that's my answer to why C++ doesn't have garbage collecting. It's a good language for writing a garbage collector in for applications where that is appropriate, but this is not it. So the type system has been a constant challenge. I said I wanted efficiency, I wanted generality, expressibility, I wanted guaranteed type safety. It's really hard to get all of those. I mean, you can't do type safe fiddling with bits. and operating system resources. So there's sort of a tension here. But anyway, look at this. I wanted uniform treatment of built-in and user-defined types because I wanted to write some generic code, and I really didn't want to have one set of rules for complex numbers, which is user-defined, and integers that we got from Dennis Ritchie. So neither Simula nor C could do it, but I thought it was essential. In C++ you can. The vector I made on the previous slides works scope-wise, type-wise, just like an integer, just has different semantics. And I wanted the user-defined types to be affordable. I wanted to be able to use these kind of techniques on the kind of computers I was having at the time. When I designed this, I was dreaming of getting a 1 megabyte, 1 megahertz computer, but I couldn't afford one. You can write C++ for very small systems because it was born there, and it hasn't changed in that respect. Type safety gets improvement. Parameterized types I wanted for generic programming. It started out with macros. I thought I could get away with doing it with macros. I couldn't. It didn't scale. I wanted class hierarchies from Simula, and got them. So basically, there is the constant pressure to improve the type system. I think my main tool is to make it more expressive. If I can understand the code, maybe the compiler and the optimizer can too, and you get it fast. So basically, improving the expressiveness of the language actually reflects what you need to do to get it to run faster. A lot of what we do has been to move computation from runtime to compile time, and you can do many things, probably more than you imagine, at compile time in exactly the same way as you do it at runtime. And if you do things at compile time, you don't have to write an error handler because the compiler tells you not to run that code. If you do it at runtime, you have to do error handling in some way or other, and that's always the worst part of a system. Tighten the type system to improve optimizers also. Create a memory model for concurrency. We're still working on that. We have all the basics in place in the standard, but we really want to do more, and there's people working on it. And basically, this early decision that we work on improving the abstraction mechanisms rather than building in solutions to problems has held over the years. And whenever we find there's a lot of errors of a given type, we probably can't ban it because it's fundamental in the language and it's been around for a long time, but you can provide an alternative and then provide ways of detecting the bad stuff. I will get to that eventually. So there's the abstraction mechanisms in the language. There's the usual functional abstractions where we can run functions if they are pure functions without side effects. We can run them at compile time instead of at runtime for optimization, or we just want them general. We have classes to build user-defined types. The ideal is that you can build user-defined type that runs as fast and is used in the same way as built-in types. That's where you get the zero overhead, RAII, hierarchical organization to do classical object-oriented programming, and parameterized abstractions to support generic types and functions, which basically is the foundation of all the generic programming in C++. And looking at generic programming, that took a long time. I started with macros. I believed that would work. I was wrong. But I had the right problem. And quite often having the right problem is more important than to have the right solution. So we recovered eventually. In 87, and there I wanted something extremely general and flexible. The design aim explicitly at the time was I want something that can do things much more than I can imagine. The assumption was always that if you take a group of people like this, they will have better ideas than any individual. They certainly have more ideas, and you have to take that into account. So extreme generality flexibility, it has to have zero overhead. So for instance, I don't want a virtual function low-level memory accessor, like a subscript operator, because an indirect function call is inherently overhead. And so you have to have zero overhead here to have it useful for that kind of stuff. And of course, I wanted well-specified interfaces. The function prototypes in C came from my early work, and it's been in C++ forever. And so obviously I wanted similar kind of error checking for these very general abstraction I wanted. I couldn't get it. There was 3 things I wanted. Nobody knew how to get all of the 3 things back in '87 or even much later. And so we got the 2, and people have suffered from bad error messages and complex code ever since. But people aren't stupid. They're suffering like that because it delivers something important. So the problem is how to make it easier and simpler, and that's what we've been working with. The solution is called concepts, which are specifying the the requirements of a template on its parameters, and classifying the parameters in a way very similar to the way we specify the argument to an ordinary function. So that ships, and it goes back to the principles. You can find them in the design evolution of C++. Generality, zero overhead, provide good interfaces. So I'm going to show you how you use the concept from C++ 20. It's shipping with all the major compilers. The implementations are not really perfect in all cases, but they are pretty good. And this is standard, they're improving. So basically, what we want is generic programming to be simpler, safer, more flexible, and faster. And let's see here, vectors. You don't want a vector of a specific type all the time. I mean, if I had a vector in the language that was only vector of doubles, it would only make some physicists happy. I want a vector that is parameterized on its vector type and possibly on its element type and possibly other things. So here we have a vector. We're deducing that it's a vector of integers. Here is a vector of something that happens to be a vector of C-style strings, which is pointer to constant sequence of characters. And you can use Q-sort to sort these things. So this is the old way, and this is quite error prone. There are 2 integers right next to each other, and I sometimes flip them, so I get the size and the number of elements wrong. In C++, by using abstraction mechanisms, we can do the simplest things, sort my container, and that should work. Now, some types are really ill-behaved, like C-style strings, that doesn't actually compare the contents of the string with equality. It sorts. So we can provide a function here, an operation, it's a lambda, to do the comparison and add this to the stuff. So we have flexibility. A vector is parameterized on the element type and on the kind of container it is and the operations that it's doing. So here's an example, C++ 98 style on constraint templates. This was the way we wrote code for about 20 years because we didn't know how to implement something better. I'm saying that there should be a type, which I called random access iterator, and sort takes 2 of those. And then we write code hoping that the type we fed to the call of sort really was a random access iterator. And some of you have tried, and you know that the error messages when we make a mistake here are horrid. Okay, in C++ 20 we can use what's called concept. We simply define what is required, And for sorting, I want a sequence that is a sortable range, and we will define what a sortable range is at some point. And now I can sort it, and I'm actually implementing the sort with the old style implementation here. So this gives us a simpler notation and a better checked implementation, more easily to optimize implementation. So that is how we move from this level of abstraction to this level of abstraction. I can now say sort a vector, assuming vec is a vector of something, and sort a list. And it won't do that because the C++ standard library sort function requires random access, because it's far easier to write a good optimized sort function if you have random access, and lists don't provide random access. I mean, if it did, you could have somebody make a list of 100,000 elements and trying to subscript the last one. That's not a good way of writing code. Okay, so now the problem then becomes, and has been for years till we solved it, how do we specify solvable range so that it is really general and doesn't cost anything at runtime? Okay, this is how we do it. A concept is a compile time predicate. It's basically a compile time function. I talked about moving things and functions to compile time. This is a compile time predicate, returns a Boolean. After checking some properties of some types maybe, it yields a bool, usually built from other concept, and of course it has zero overhead because it's just part of the type system once you've defined it. So here's a sortable range. It is a random access, so R is a sortable range. If it has random access, it's a random access range, and it provides iterators that are sortable. Random access range and sortable and iterator underscore T are part of the standard library, so you don't have to invent them. Now, if I wanted to sort lists also, I just define my own here, sortable forward range, which is a forward range, and the elements are sortable through iterators of the right type. So basically the difference here is I have the random access operations, and I don't have the access operations there. And now, whoops. Okay, yeah. Go back there. If we had the sortable range definition, this one would now work. Basically, the vector has all the properties needed for a random access range, so it will work. This one, you soon find out, doesn't have all the properties because there's not random access, but it does have this one, and so we can pick the function that we could now write based on this one that does the sorting of a list. My simplest implementation, how do you sort a list? You copy the elements into a vector, you sort them, and you copy them back out again. Don't have to be clever for this. Okay, so a language is only part of a programmer's tool chest. When you listen to people and when you look at the web, there's a lot of people that think that the only thing that matters is how beautiful the definition of the language is. But when you write real systems, there's all of these other things that matter. And so you need a community around a language. Code is written by people for people. And you need a lot of tools and education stuff, analyzers, libraries, etc., etc. I don't think we ever get enough of these things, but there's a lot. And this is the boasting slide. C++ is very often used for foundational purposes. That is, you don't see them. Even people using the systems don't see them. I mean, some of you might like JavaScript, so it's a C++ program. Graphics, if you want to run a helicopter on Mars, there's a library for that too. So anyway, let's get on with this. Code organization and compile time are important things. We have moved more and more things from runtime to compile time, meaning that compile times have grown a lot when runtimes have gotten shorter. And so the old header file and include technique is a hack. It always was a hack, but it seemed a very reasonable hack back in 1972 or there, when it was invented. And nobody imagined things like the header-only libraries for C++. They're really a pain. And the major problem with the header files and includes is that an includes is intransitive. So an include includes something that includes something, and if there's anything in there, it can get in your way. And it leaks information between the headers. Not good. Much repeated compilation, include an include file in 100.c files, and you compile it 100 times. This is not great. So it doesn't serve templates well, and well, yes, the header files are much bigger. Modules in C++20, import is not transitive, one problem solved. Import followed by another import is the same as the opposite direction. We can now compile modules in isolation and use them in any order. And that basically means that you can do a lot of computation once only. And that is important. But changing source code organization is very hard. And it takes some time for the tool change to build up around it, like the build systems, the package managers and such. But this is where we're going to go. And the reason is I'll show on the next slide, but basically it gets more elegant code. Here is a one slide example. I want to build a module called a map printer. I include a lot of stuff that I need for implementation. And then I use it to write a code here. I say I'm exporting this print map function. That's all I'm exporting. I am not exporting the whole I/O stream or the containers, which is one of mine, not standard. And I'm most certainly not opening the code to the whole standard library. This is not transitive. There is the effect is quite dramatic. So I did a little experiment of a module which is called STD, which has been, it's almost certain for C++23 because it's been voted out of the language design group, the evolution group. And so I try including hello world or import STD. And so here I take the needed header, which is just I/O stream, and I compile it, and it takes a fraction of a second. I try to do the same thing with import XTD, and it takes a tenth of the time. Now, STD holds everything from the standard library. In other words, more than 10 times the amount of stuff in I/O streams. And so we just speed it up with a factor of 100. This is not bad for improving compile time. This is a great carrot for people to change their code a bit so that they don't have to sit and wait and drink too much coffee. I did a slightly less extreme example. A mix took 9 of my favorite headers, used them ever so slightly, and see what happens. And yes, it's only a factor of 5 here. I think you should guess maybe a factor of 7 for realistic systems, or 5, 10 and such. I have seen real code that didn't improve their compile time speed from going with from include to modules, and I've seen 100 times improvement. But this is it. There's a paper there that describes this experiment. And so basically, it comes to education. You can't just say, here's something new. It's great, go use it. You actually have to say, well, here's something you might like to use. Try and figure out what it is. Here's the description. Try and figure out how you can use it. here's examples of use. There's an education process, and the point of language design is actually to change the way we think, to change the way we build our systems. And people are quite resistant to that. They are familiar with something, they're comfortable with something, they don't want to go to something new. Something new is quite often seen as necessarily complicated and slow, whatever it says in the paper. But we confuse the simple and the familiar, and we should go for the simple. Not invented here is another problem. So how do we actually write modern C++? We have to avoid sort of being very excited about every little obscure detail that's coming along. I strongly recommend that people experimenting with the new features to see how they fit into their world and see how it addresses their problems, rather than just going in and use it because it's fashionable. I mean, there was a time where people were building, everything had to be a class hierarchy, everything had to be a virtual function, maybe a virtual overloaded operator or something like that. No, that's not the way you build things. You see what the problem is, you see what your solution is, and then you see how you can best represent it. We've been trying to get some guidelines called the C++ core guidelines, even got a logo, and we distinguish between what's legal and what's good. We need stability over decades. We cannot break your old code, but we can provide newer ways of doing things so that it's possible to evolve into a better use. And the C++ core guidelines, you can find them on GitHub. It's a set of rules that should help people use modern features well. There are static analyzers that backs this up so that you can get, say, memory safety by following these rules and have it checked. So basically what we have come to here is there's some foundations of C++. The static type system will equal support for built-in and user-defined types. One of the early ideals, we're very close. I mean, we can build our own literals, for instance, these days. You must have value and reference semantics because we want the high-level value semantics, but quite often we need the messier reference semantics to implement it. Systematic and general resource management, efficient object-oriented programming, generic programming, flexible and efficient, move things to compile time, and make sure that it's still C++, direct and efficient use of machine and operating system resources. And if you want to look at this from a historical point of view, from a design process kind of view, there's some history papers. I have presented to the History of Programming Languages conference 3 times. This is a record. Nobody else has done 3, and no other language have gotten 3. So that's that shows that we both have evolution and stability. And so, questions? I did manage to talk so fast that there's time for questions. If anybody has a microphone, it will probably help. Otherwise, it might be an idea to be close up here. Ah, there's a microphone. Is it turned on? Not really. Try yelling.
Okay, so my question is about models. You said that it can help 100 times with this includes of standard libraries. Okay, so it started working. But have you any data for real projects with million lines of code which transition from this pre-C++ 20 era to modules?
Not quite sure I understand the question. The problem is not so much the implementation of modules. If it's done well, it's actually done pretty well in the Microsoft implementation done by my friend Gabriel dos Reis. You can transfer large amount of code into modules. You can modularize the standard library or wider libraries. There's some embedded systems libraries that's been done in Germany that's been transitioning, and we have consistently seen massive improvement. Think factor 7 in
my question is about numbers. How big is this improvement in this real world?
How what is it?
Projects. How faster they compile?
All compilation figures are relative to the alternative using includes. So when I said 7 times, it is if it took an hour to compile the old stuff with includes, we're talking about 10 minutes.
Okay.
And by the way, I predicted that it would have exactly the same runtime code, runtime times. As a matter of fact, there's some signs that the combination of concepts and modules lead to slightly faster code. It gives more information to the optimizer. The problem is that not all build systems has been upgraded to do modules very well. So experiment before you start going into large-scale conversions.
Yeah, so Bjarne, what is your single largest regret in the evolution of C++, if you have any?
Well, regrets are the wrong word. I knew I couldn't do it perfectly when I started. I just didn't have the resources. I tried to eliminate the C style conversion both ways between types, fundamental types. I tried to make sure that I tried to clean up the C-style problems, and I failed. There was just too much C code, too many people were keen on that. If I had a time machine, I could go back and try and talk Dennis into not having all of those conversions, not having conversions between unsigned and signed, which is a very bad bug source. My recommendation is not to use unsigned except for bit fiddling. The other use of a time machine would be to go back to 87 and explain concepts to me, and then I could make a better implementation, simpler then, and we wouldn't have had so much trouble with early templates. You see, when you think about regrets and things you should do and could have done, you should think about the world then. And I am very loath to say, going and imagining telling Bjarne vintage 1990 how he should survive the next couple of years under pressure from all the languages and such. He knew that world much better than I do today. And you have to see what can work. What do you do if you only have 1 megabyte of memory and only 1 hertz, and you need to generate high quality production code with a compiler living in that world? That puts constraints on what you can do. So I think none of the major features of C++ are mistakes as such. But every major feature, I think I could do much better today. So the foundations are sound, but there's a fair number of barnacles hanging off the language. And that's why I'm working on the core guidelines project, which is to say, how do you avoid the barnacles? How do you actually write good C++, maintainable C++, type-safe C++, and preferably have checkers that can make sure that you actually follow your own rules. Okay, I'm being timed out, and I hate to go with questions still hanging, but I have to catch a train. And so I must obey the rules here, so thank you.